Good afternoon.
Good afternoon.
Hey guys.
Hello.
Good afternoon.
Hey David.
How's it going,
Hey
Moshe?
Matthew. Just fine.
Hello.
Hey Matthew.
What's up?
Aren't you Jewish?
Yeah.
Well, Shana Tova.
Yeah.
Happy New Year.
Yeah. Had some round challah funny last
Shana Tova. Shana Tova, Moshe.
Shana Tova, Michael. Or
Oh,
should I say Michael?
oh, you use the Sephardic pronunciation. The rest of the people don't know what we're talking about.
Yeah, secret.
David, do you know what Lashana Tova means?
No, I don't.
It means good year. It means it's like Happy New Year in Hebrew, because
Okay.
this is the new year.
My wife is cooking the food for my son to come over
Oh, all right.
for New Year.
Can you ship some over to us? We're hungry.
Yeah, okay, but I'm leaving here at 3 because I have to go do that.
Sure. Yeah, I always like how like the Jewish New Year starts in like the fall, and then the Jewish day starts in the evening. I just think that's kind of interesting.
Yeah.
Out of phase with the I guess.
Actually, what is even more surprising is that the Jewish year starts on the first day of the 6th month. Why it doesn't start on the first day of the first month, I don't know, but
The calendar has to do with whether or not the people were nomadic or stationary at the time. The ancient Hebrews were a nomadic people, so that the months, they used a lunar calendar. The months did not have to align with the seasons. Once people became agricultural, obviously the months had to align with the seasons, or else your planting would get screwed up.
Matthew, you might be interested. Again, Abner Shimoni wrote a book about a boy in Italy who lost his birthday when the Pope moved the years, and how he petitioned the Pope to allow everyone who lost their birthday to celebrate it all on one day.
I had no idea.
It's a children's book.
Which Pope was that?
I have to get that.
Which Pope was that?
Which Pope?
You'll have to buy the book to read it, Michael.
I gotta buy the book.
Oh, okay. When you bring the food, could you also leave some money so I can buy the book?
Huh? How about that? Oh yeah, is it this one? Tibaldo and the hole in the calendar. Haha, yeah, look at that. That's awesome. Yeah, I'm gonna have to get a copy of this. I wanted to mention this thing that you guys might be interested in. Have you heard of the Quantum Week of Fun?
Fun or fund?
Fun.
Fun?
Yeah.
It's not fun.
Just
We're
fun.
here we're all masochists. We're here for the torture.
No, quantum fun means you get only a little bit of fun, tiny little bit of fun. That's it.
Oh, it's probabilistic whether or not
Fun is
you get-
quantized.
Yeah, and it's probabilistic. Usually you don't get it.
Your fun is definitely entangled with other people's fun.
Yeah. Well, it is in a singlet state. They get it, you don't.
Quantum fun. It's all blurry. My eyes are going.
Yeah, apparently Well, you know, there's this company, Cambridge Quantum Computing. They do interesting stuff. It's the British Cambridge. And next week, they're having a whole online conference, which, you know, is free to go to. You can like sign up on this Eventbrite page. And, you know, if you sign up, you get like access to like a Slack channel so you can like chat with people, I guess. And, you know, there's 4 days. They have quantum algorithms, compilation, quantum chemistry. I'm most excited for this day. Quantum natural language processing. I've like alluded to this from time to time, but you know, I've never done like a little meeting on it. But we should at some point, maybe after this. Very interesting. I mean, for years, people have been like, it'd be great to, you know, apply some of that quantum formalism to language or cognition, you know, and people have had mixed results with that. But more recently, there's been very interesting results, especially from the angle of just like, well, how could we use quantum computers to do very fast language processing? And, you know, our friend Bob Coca or whatever, who, you know, is behind a lot of the string diagram stuff we talked about way back when, is really big on that. And so he and a bunch of, you know, collaborators and seems like, you know, people associated with like their group at Oxford are giving a bunch of interesting lectures, quantum algorithms for natural language processing, redrawing grammar as compositional circuits. So yeah, you know, I recommend checking.
Pat, is this on Quantum Appaloosa? You follow that, don't you?
Oh yeah, I haven't been on there actually.
Because I didn't see it. It's not posted yet, as far as I can tell. You know, Terrell France, who sometimes
Yeah.
he runs that. It's out of the University of Harrisburg. Yeah, right. The last time I looked, I don't think that was posted.
Yeah, it's so nice that oh look, there we are. Haha, so cool.
It starts on Monday.
Yeah. Yes. Well, wait, when was the 21st?
Monday.
Yeah, Monday. Yeah, although, you know, the first talk is like at noon UK time, which I believe is like 7 a.m. You know.
They sometimes have these talks out of India, so it's like in the middle of the night, our time.
But yeah, you know, if you guys can't make it, then at some point in October, I'll do a meeting talking about some of this stuff. We can look at, you know, these guys released a really cool software framework a couple of months ago called DiscoPy, which, you know, lets you use Python to play around with string diagrams and, you know, assign like functors between, you know, different aspects of these diagrams to vectors in like some semantic space or different, you know, that corresponds to the meanings of different words and stuff like that. Like this, for example, classic kind of diagram in the game. Talk about it. But this is, you know, this is a fun, very elegant little piece of code that they have here. Anyway, yeah, and actually, you know, today we're going to talk about, you know, a little, like, very, very gentle introduction to some stuff about, you know, quantum field theory and curved space, and how people disagree about, you know, what kind of particles there are, depending on their state of motion. You know, next week, ideally, I was thinking we would return after a very long time to kind of where these, you know, meetings restarted back in the spring. We were talking about wormholes. You know, what we'll be talking about today will kind of nicely segue into that. Next week, we'll talk about, you know, basically the same kind of wormhole model that we talked about way back when. It just basically involves, you know, two black holes, they're entangled in some way. Something falls in, it gets scrambled up, and then there's some kind of coupling between the outsides of the black holes that leads to the interior being traversable. And it involves, similar ideas, and we'll see it in a different context, namely in the SYK model, which, people love because it's simple and you get a lot of cool effects from it. So that's what's coming up. And I just mention it now because insofar as we return to that, we'll return to talking about, cool diagrams that look like this. But that shall come in the future. Yeah, I recommend the Quantum Week of Fun. You know it's going to be good because they had such a great logo.
Matt, can I ask a question up front?
Mm-hmm.
A very impertinent question.
Oh, carry
I
on.
do not believe in Hawking radiation the way it's described, and I'll tell you why. I hope you can answer this.
Probably not.
I
But
believe in the Unruh effect, which I believe you're going to cover. Can we not interpret Hawking radiation merely in the eyes of the Schwarzschild observer? That in fact, it has to do with the acceleration away from the black hole by the Schwarzschild observer, rather than the black hole emitting radiation.
well, the way that I understand it is that, like, yeah, the Unruh effect and the Hawking radiation are like basically the same effect, but in fact, in the Hawking case, it's actually like a stationary or like inertial observer far from the black hole that sees the radiation.
Or
Accelerated observer in the Unruh picture that would see the radiation.
Or it doesn't have to be far from the black hole. The thing is, in order not to get sucked into the black hole at a finite distance from the black hole, you have to be accelerating away from it.
No, it is very subtle. It is true that the two are very much related. But what Matt said right now is critical here. This is the radiation seen by an observer that is infinitely far away from the black hole. And normally, this observer will see nothing. If it was just the usual Hawking radiation, when you are far away from the black hole, far enough, you don't see anything because indeed you are not accelerating anymore. And this is one point that, quite frankly, I do not understand very well. It has to do with the redshift. When you apply the redshift formula, you say that the Hawking radiation is indeed the Unruh radiation for an observer that is very close to the black hole. An observer close to the black hole is accelerating away. The observer stationary, close to the black hole, sees the Unruh radiation. But then when you go to infinity, what does an observer at infinity sees? You apply the redshift formula, the gravitational redshift formula, and lo and behold, it is not zero. When you're at infinity, you see a definitely finite temperature. And for a very small black hole, this finite temperature can be pretty high.
All right, but here's the thing. At infinity, the redshift is infinite. So what radiation is there?
That's the whole point. It is not infinite. It is a very subtle point that, to be honest with you, I can follow the math, but I do not understand it. I cannot explain it. I cannot explain it to myself. I would expect indeed that the redshift at infinity would be infinite. But the whole thing about the Hawking radiation is that it is not infinite. And again, I can follow the math, but I do not understand it.
And does an infalling observer, somebody falling into the black hole, see any radiation at all?
Yeah, it's a good question.
I think
yeah,
not.
At very least, less.
I don't see how it's any different from
Maybe a little
Unruh
bit.
radiation due to the acceleration of the observer. And even at infinity, whatever you mean by infinity, there is some finite acceleration, because even at infinity, a massive object would still attract you. So you have to be accelerating by some small amount, even at infinity. And again, Moshe, I also follow the math. I follow the math, but I don't believe it. I don't accept it.
Okay, let me be honest. I've never seen a Hawking's derivation of the Hawking radiation. The only one that I've seen is in Sean Carroll's book, and he doesn't give you the original derivation. What he does, he treats the Unruh radiation in details, then basically says, well, Hawking is basically the Unruh radiation.
Right.
And then he goes to infinity. He uses the formula for the redshift at infinity, and it is not zero, it is finite.
All right, well, here's another way to derive Hawking radiation. If you believe that a black hole has entropy, then it has temperature. So if it has temperature, then it must radiate.
That's right.
But that's if you believe that it has entropy. You know, and Hawking himself originally believed that entropy is destroyed in a black hole. Then he changed his mind. But
well, I buy Bekenstein's argument for black hole entropy. It makes sense. To me, it is a convincing argument. So yes, this is another argument, but I think that the core here is indeed solving the Klein-Gordon equation in a curved space-time.
okay, but here's another thing. Here's another thing, Moshe. If you buy Hawking radiation, then by necessity, a black hole has a negative coefficient of heat. That's the only thing in the universe we know that has a negative heat coefficient. Does that make any? In other words, it can radiate. A cold black hole can radiate into a warmer heat bath. Does that make any sense? That's a violation of the second law.
No,
The second law to derive it, and then they violate.
No, you got it wrong. Right now, when you look at the sun, you are radiating towards the sun. The point is that the sun is radiating towards you a lot more than you radiate towards the sun.
No, but you're radiating.
Just because the sun is warmer than you are doesn't mean that you do not radiate.
No, but you're radiating into space. At night,
you're radiating towards the sun. Look at the sun. Go outside, look at the sun. You will be radiating towards the sun. And what you radiate towards the sun is very tiny compared to what the sun is radiating towards you. But you're still radiating towards the sun.
Okay, the net radiation during the day is that the sun radiates towards the earth and lowers the entropy. At night, the earth radiates into a colder space because it's
and a black hole radiates towards the empty space, but the empty space radiates a lot more towards the black hole. So the black hole keeps gaining energy and it gets fatter and fatter even as it radiates.
No, but it gets colder. The black hole gets colder. It's got a negative heat coefficient. It gets colder. In fact, a larger black hole is colder than a smaller black hole. It gets colder as it absorbs radiation. Does that make any sense? But according to Hawking's theory, that's what happens. A black hole that absorbs radiation gets colder, not hotter.
It's interesting.
So the analogy is not the same. The analogy of the sun radiating towards the earth is still getting warmer. The net radiation is absorption, and the earth has a positive heat coefficient. But in black hole theory, the black hole has a negative heat coefficient.
That's a good point.
That's why I don't believe this. I don't believe, and since it can never be measured, you can never measure Hawking radiation.
you know, it's interesting that, you know, people do take things like Unruh radiation, Hawking radiation somewhat for granted, but as I think we've discussed, you know, it hasn't been directly measured, although it's interesting that, you know, people are always proposing tricky ways of trying to measure it in like analogous systems where, you know, there's like an effective, you know, slower speed of light. And so this temperature.
Well, there are claims that Unruh radiation has been measured, but at least that may or may not be so. It hasn't been verified, but at least you can design a laboratory experiment to measure Unruh radiation, but you can't design an experiment to measure Hawking radiation from a massive black hole because you're talking about microkelvin in an atmosphere that's, you know,
Yeah.
Kelvin.
Well, you know, I could see in
Okay,
50 years, we
let
have
me tell
people
you how
that,
it will be measured. It is not going to be done next week or next century, but eventually people are going to make a tiny little black hole of maybe a billion, maybe a fraction of the mass of the Earth. And this is going to be a hot black hole.
Right.
You make a tiny black hole, it's going to be hot. You make
Right.
a black hole that weighs 1 billion tons, it is going to be a very hot black hole. It will have a radius of 1 nanometer, and you will fry. But this is not something that is going to happen in the next couple of years.
And when that happens, then we can believe the theory. But until then, the theory sounds like a bunch of hogwash. Like I said, Hawking himself changed his mind at least twice. So you know,
until then, what people are doing, they look for a small primordial black hole. During the Big Bang, people claim that the small black holes could have resulted from local compression of the gas. And if you have created the tiny black hole during the Big Bang, at this point, you should be able to detect its radiation. So far, no such small black hole has been detected.
I mean, it'd be pretty interesting if you were right, Michael. You know, like if after, you know, 30, 40 years, you know, they get a chance to actually measure these effects and don't find anything. It really would, you know, send shockwaves through the.
No, but this is
Of this stuff. There's like a lot of stuff that's built on this structure of, you know, things like the Unruh effect and the Hawking radiation.
Well, again, the Unruh effect.
Wrong about that. It'd be very interesting because
the Unruh effect makes sense because the Unruh effect is merely transferring energy from the acceleration to what is apparently particle creation. But Hawking radiation, I mean, at least to me, doesn't make any sense. But it's another one of those theories that, and it's not whether or not I believe it. Hawking did not believe it at first. Hawking said that entropy is destroyed in a black hole. That's what I believe. And until proven otherwise, I think that's what we have to accept. But of course, I'm outvoted, you know, like 99 to 1 at least.
Yeah. Well, you know, just you know, depends on your priors. You know, is your prior like quantum mechanics is probably true? Or is your prior?
So we can prove this by Bayesian analysis.
Yeah. All right, so let's get started. You know, this discussion we just had was very good. You know, I have to say that you know, many of you probably know more about, you know, this topic than even I do. You know, what I was just going to try to do today was just, you know, give like a very simple introduction to some of those ideas, just from the perspective of, you know, we've been talking about oscillators, second quantization, the notion of an indistinguishable particle, and you know, what I wanted to focus on today is just this idea that, those particles, those quanta are dependent upon, the observer state of motion who's going to measure them or whatever. As we've talked about, what is an atom over the last couple of months, we keep seeing the way that stuff, which at first, you could say seems like a thing, ends up being some kind of relationship, and people can disagree, but there's some way of unifying the perspectives. With that in mind, if you'll allow me, I was going to give I've often been encouraged to give more context to, what we're talking about. So I thought I would give like a recap of, the story so far or whatever. Okay, this may or may not be interesting to you, from like a little philosophical thing, but, I just wanted to talk a little bit about like the style of exposition here. I'm calling it a dialectic. I don't know if that bothers anybody. Like in Greek, say, Socrates would have engaged in dialectic. He hangs out in the forum and chats people up. And he doesn't so much have like a consistent theory to propose, but is interested in like hearing how people use words and like finding the contradictions in those words. And, through a kind of dialogue, like deconstructing, people's preconceived notions with the idea that in some way by, slowly rearranging how we use words, we can get closer to the truth. And as he says, carve up nature at its joints, figure out exactly like, well, how should we use words? What's interesting about a dialogue, as opposed to a monologue, think of a monologue as like the classic notion of like a mathematical discourse where you start with some axioms, rules of inference, go forth, prove some theorems. In some sense, the conclusions are contained at the beginning in what you assume. And the, purpose is just to sort of bring out the implications of your definitions of what you've said. In contrast, kind of like dialogic or like dialectical exposition is more about, how concepts bounce off each other and evolve in time. And, that kind of discourse is most useful when, people are bringing to the subject preconceived notions, or in some ways, people's already existing ideas have to be rearranged a little bit in order to communicate something, as opposed to the situation where you're just trying to deliver new or useful information in a sequence. The most famous, one of the, you take a philosophy class, you hear about the dialectic, you're going to think, oh yeah, there's that German idealist philosopher Hegel. It's very much associated with this idea of dialectical thought and, the caricature of his way of thinking. And, these terms are kind of, I would say, like intentionally vague. The way he thinks is like, you have a thesis calls into existence its antithesis. And then the thesis and antithesis are overcome by a kind of synthesis, which resolves them, but at a higher level in a way that couldn't be anticipated by mere analysis of the thesis and antithesis, which are by definition irreconcilable. And then a new cycle begins, the synthesis itself acting as a thesis, bringing forth a new antithesis. And for him, it's like, what the fuck is a thesis or antithesis? Maybe it's an idea, maybe it's a state of consciousness or a material situation. It's sort of vague. But, he famously uses this as a sort of rhetorical or narrative device to attempt to retell human history as part of the dialectical unfolding of ideas in a kind of cosmic spirit, whose intellectual development tracks the changes in the structure of the material world, whose ultimate aim is self-knowledge. A classic of, German idealists, like 19th century thought, and then it gets turned on its head, as many of you may know, by Karl Marx, the young upstart who decides, I'm going to apply this same kind of reasoning to economics. Screw Hegel, he thinks ideas are so important, but I think ideas, follow from the material structure of how we, barter and exchange and whatever. So then, in the 20th century, someone says like, you got to engage in some dialectic that has like all these political overtones because, Cold War and all that. All that aside, I mean, I think that math really benefits from a dialectical exposition because on the one hand, math is very conceptually unified. And so, it's like, there's a real question about like, at any given, trying to communicate something, where do you even start? Mathematics is like the true heaven of coincidences. Everything is popping up again and used and reused and resonates across different scales. And to grasp even the importance of simple things, you really have to scale mountains and like have this larger context. And there's so much that it's like, you'd like to proceed step by step, proving everything as you go along, but, getting lost in the weeds often makes it hard to grasp the longer arc. And yet to elide over details allows misunderstanding to creep in. So that's just sort of like a pedagogical thing. But on the other hand, like we've talked about, you have things like in mathematics, Gödel's theorems, which show that you have a sufficiently complicated formal mathematical system, it can't coherently talk about itself. You need another perspective, some kind of higher vantage point, some other formal system to analyze it from. And so, sticking from some sort of fixed formal system or fixed set of ideas isn't going to get you far enough. More empirically, it's like physics is always tugging mathematics by the hand, establishing empirical correspondences that couldn't have been deduced by pure analysis alone. And so, for all those reasons, like I would say, I remember years and years ago when I first read Hegel or whatever, I was like, this is kind of cool, a little abstract. But you wonder, is there anything really that, like, what's a good, like, example of, like, the Hegelian dialectic, like, that's not controversial? You know what I mean? And I would say, personally, like, I think that, the sort of derivation of our, like, the sort of the number system is actually a really good place where these kinds of dialectical ideas seem to be kind of like appropriate. And so that's sort of, influenced how I've, organized a lot of these lectures. So, to give the overview of it all, we started by talking about the basic idea of a pebble. Could place a pebble somewhere, we could take it away. To communicate with the pebble, we had to agree on whether presence or absence would be significant. So we realized as much as we're talking about a theory of quote unquote numbers, we're really talking about a theory of symbols, which you can place, erase, symbols symbolizing other symbols. And there's rules, and you got to follow the rules, because by following the rules, you can make sure that, communication via those symbols will be reliable. But then you go on, you say, well, we have a pebble, why not have another pebble? Why not put another pebble there and another one and another one? And you get a little pile of indistinguishable pebbles. So you get the counting numbers. Got to agree on, what number you start counting from. And you can look at a pile of pebbles as a kind of contextualization or context for the original pebble. Like, oh, this is actually the fourth pebble, if you've been keeping count. And to keep count is just to build up a little pile. Go on, you imagine counting, iterating counting itself, counting all at once, boop, and you get addition or combining piles. And the demand that for it to be a number, we have to have some kind of like inverse operation. What happens if you have addition, you have subtraction? What happens if you subtract past zero? You got to invent a new kind of number, the negative numbers. And so you achieve a kind of synthesis, the integers. Communicate with an integer, you have to agree on what's zero and what sort of direction you're in, positive or negative. Keep going, iterate addition to get multiplication, whose inverse is division. The synthesis is, the rational numbers. or piles of prime pebbles. You can contextualize now a pile of pebbles by specifying like a rational number that translates between your units and my units, or different ideas of one. And if we allow division by 0, you see that the number line, gets wrapped around a circle. We iterate multiplication to get exponentiation, whose inverse is root taking. We get a whole new, playing field.
Matthew, can I stop you? Can you just go back?
Oh yeah.
It's so reminiscent for me because I took two courses actually from a guy named John Finley, who was a famous Hegel scholar.
Oh yeah.
The second one was on Hegel's Encyclopedia, and exactly what's happened then is happening now. So go back where you say that the rational numbers are a synthesis. Tell me what the thesis and antithesis was in that case.
Yeah. Right. So, the idea is like you start off, like the thesis, I guess, would be like the integers. And then, the antithesis arises because you're interested in this operation of continually iterating, right? So initially you have this idea of just like putting a pebble there. You iterate that.
So the thesis and antithesis are not on the same level. One is an object and one is a description.
In this case, yeah, I guess the way I was looking at it is that, to the extent that you have like a number system, there's got to be some notion of like a root or like a 0, in the sense that, it's like if I'm here on the number line, like that only makes sense if it's with reference to like, oh, this is like the 0 point or whatever. And so, that translates into the notion that like if I have like a number like, 2 or something as like a rational number, I got to have a number like 1/2 that, will cancel out with 2 to give 1, so that we can then use those rational numbers to like agree about, what we're regarding as 1, or in the case of integers, what we're regarding as like an additive.
So you just move from addition to multiplication there?
Yeah, exactly. So, once you...
What does cancel out mean? That 2 gets canceled out by 1/2. It means that, it means that the multiplicative operation achieves its identity by a number times its inverse. That's the 2 times 1/2.
Yes, yeah,
So
exactly.
you just moved too fast for me from addition, subtraction to rational numbers. So I did not see that. Again, this is all, I don't say you can't talk like this. But my experience is that if you focus down on any particular step, you quickly become confused about what's being talked about.
Yeah, I mean, I don't disagree with you. I mean, I'm not proposing this like a formal theory of mathematics. It's just more like I see that there's a kind of dialectical pattern here. And I think that, there's lots of ways that you can kind of divvy this up to kind of get that pattern. It's more about pattern recognition here than making like...
Matthew, let me try to rephrase what you said right now, just to make sure I understood it correctly. Let me first say that this is the first time that I hear about Hegelian dialectic, and the way it works here is, from this specific example, is you start with integers. You have integers that they've been clearly defined, and you use this as the thesis. You have multiplication, and you still have integers to deal with multiplication. And this is still the thesis. But then if you have multiplication, you must also have division, the inverse operation. If you have division, then all of a sudden, integers don't do the job. And this is the antithesis.
Yeah.
This is the antithesis that shows you, hey guys, integers are just not it. And then the synthesis is rational numbers.
Yeah, that's exactly.
Together you get the rational numbers, and that's the synthesis. And then you are going to have another step where the rational numbers don't do the job. and you will have decimal numbers.
Yeah, that's exactly how I was thinking about it. Now, we'll see, like, as we, you keep going on, it gets a little bit more vague. You may know that, so like in the next thing, right? It's like, if we iterate multiplication, we get exponentiation, whose inverse is root taking. We get irrational numbers, we get complex numbers. But then, if you keep, so what's iterated exponentiation? Traditionally, you can go look it up on Wikipedia. It's called tetration. An iterated exponentiation. I mean, that's how some people think about it. You can define these, a whole hierarchy of so-called hyper operations that, in the more traditional way, continue on this idea of iterating basic arithmetic operations. And
So Matt, can I ask a question regarding imaginary numbers?
oh,
Wouldn't you say that rather than they considering them as numbers, they're actually an operation? They're a rotation.
well, you could say that about all the other numbers, right? It's
They're
like
operations.
a rational number is both a point on the number line, but it's also, a map between your units and my units. Like an integer, it's both, a point on like a gridded out number line, but it's also a transformation that takes, one point on the number line to another point on the number line.
So let me just say something about the word also. In my view, what we're talking about here is we have formalisms that we use to model certain situations, and they can be appropriate models or inappropriate models. But oftentimes, the same formalism is the appropriate model of different situations. And so that's what I take to mean by what you just said about also. There's the pebbles and there's the processes. And it so happens that similar formalisms can be applied to different situations, to both the pebbles and the process.
Yeah, sure. Yeah, I think that's fair. That's in the way that I'm talking, it's almost like there's a duality. You could look at like, what is a pebble? It's a thing. Or you could be like, no, it's like an invitation to remove it. Like for the pebble to be there, you could see it as like the concretization or like the, a symbol, which means you can do something, which is take it away. And the absence of a pebble would signify an invitation to place a pebble there. You could do a whole thing where, things and actions are kind of dual to each other, which is, one of the deepest kind of mathematical patterns there is. I'll say that, like this dialectical story, especially as you point out, Andre, is, it's a little bit vague, and I fully accept that. And I think that you could tell other kinds of stories using the same material and similarly find interesting sort of dialectical logic. I make a particular choice, right? Like instead of, when I iterate exponentiation, instead of going to tetration, which would be like what, a mathematician would normally do, considering these hyper operations, instead, I start talking about polynomials instead, where, thinking about a polynomial as like a pile of unordered complex numbers. Is that really the best, sort of synthesis of that idea? I don't know. It makes sense to me at some level, but again, this is, it's, I'm not investigating, like Hegel would have like invested this stuff with a weight of like, well, this is like the true veridical notion of like how the mind of God, came to understand its like nature as number. But, I'm not going to go there. It's like, this is just one story. And I like it because you're trying, in telling a story like this, you have the opportunity to link up, the very familiar and simple, addition, subtraction, to the much more rarefied, like we'll get to, vectors, matrices,
So
tensor.
Matt, do you believe that nature, or the mind of God, whatever you happen to believe, do you believe that nature uses numbers and math, or is this merely a construction of the human mind?
Well, I think it's like, I can't say that everything in nature is governed by numbers.
Anything, is
I
anything.
would say that the things that we can consistently communicate accurately about, we use numbers to do that. If there's something that we can't communicate about, there's not going to be numbers.
But if nature has a mind, let's
there's
say,
numbers.
hypothetically, if nature has a mind, or if there is a God, supernatural mind, do they use what we would call numbers? Or is that just our only way of explaining things?
Michael, let me try to answer your
The
question.
word use is very critical.
I don't claim that I know God personally, but I think that we can look at the one fraction of what this would be. What I believe is that there is something like a general accountant in nature that makes sure that we balance the books. For instance, when we create a particle, we don't create charge. We create as much positive charge as negative charge. We do not create spin, as much positive spin as negative spin. We do not create baryons. We create as many baryons as antibaryons. Why this happens to be like this, the only explanation that I have is that there is an auditor general who makes sure that at every single step, the books are balanced. Now, does this auditor general use numbers in order to balance the book? Does this auditor general say, okay, we've created here 3 positive charges, so we need to create 3 negative charges? This I don't know. I don't know what system this guy is using to balance the books, but I know that the books are balanced to some extent.
And here's the alternative explanation, Moshe. We have conservation laws.
Yeah, that's what I'm talking about.
That balance the books, regardless of mathematics.
Yeah, that's what I'm talking about. The Auditor General makes sure that the conservation laws are being obeyed. This is what I mean by balancing the books.
Yeah, and according to NERSA, these conservation laws are paired with symmetry principles, and symmetry principles depend upon the language in which you're talking. Things that are symmetrical in one language are not symmetrical in others.
But symmetry doesn't depend on math. We may use math to describe symmetry, but it doesn't depend on it. It's just a natural phenomenon.
Math is, it's like an analogy. It's like, the mathematics gives you, rules for shuffling symbols around. And it's like analogous to whatever nature is doing in its bookkeeping operations. Whether nature like is numbers or made of numbers is kind of irrelevant, in a sense, if, like the relevant thing is that the numbers provide a good analogy. Because again, there's what nature's doing. There's like math considered as such, like these rules for a formal system, and then there's us as human beings, and our particular experience of like mathematics, like as such, like we're in 3D and we're like writing on a 2D piece of paper and moving these symbols around and stuff like that. If we
what I think,
it's like a sort of.
What I think is that mathematics is our inability to conceptualize what's actually going on. It's the only way that we can describe what we see, but it's not the way a higher level intellect, let's call it nature, would describe it. And in fact, we get hung up like with quantum gravity. We're hung up because we don't have the mathematics. We may have to advance beyond the mathematics we use to describe something like quantum gravity if it exists. I think that mathematics is just our partially effective way of describing things.
I don't, yeah, I don't totally disagree, but I would say this, that, you know, it would be one thing if mathematics was just like a isolated set of techniques that people had like developed to help them like predict things. But, you know, like I say, you know, math is so unified, and, you know, like you see, you know, like the whole thing we've talked about, you know, like say with spin systems where, you know, you interpret the roots of the polynomial as these little quanta living on the sphere and stuff. I mean, what I find so cool about that is like, you could have explained that to like, you know, a 15-year-old taking algebra 2, you know what I mean? Like in high school, you'd be like, yeah, they're like, what the fuck do I care about polynomials? God damn it. You know what I mean? Like, why are we even doing this? Complex roots? Like, fuck that. You're like, oh, well, it's interesting because this is the exact structure of a quantum spin. That's kind of cool. Like, in other words, people invented polynomials or whatever, playing around polynomials, hundreds of years before it became clear you could interpret them in this physical way, for example. So that, you know, we're constantly like discovering things in different orders, and, you know, mathematics is anticipating physics and physics is anticipating mathematics, like, you know, and oftentimes, you know, hidden in the simplest things, you can see actually, you know, all sorts of crazy implications, you know, down the road. So, you know, and like, you know, and on that note, you know, for example, you know, you're trying to think about like, you know, if different organisms or beings would also have the same mathematics. I mean, I think it's sort of like, you know, like Carl Sagan has that line about how like, you know, we would use prime numbers to communicate with aliens or something, because it's like, you know, anyone who understands anything, you know what I mean? Anyone who can count is going to be like, oh yeah, prime numbers are the interesting numbers. And so, you know, you could use them as a basis for communication. You know, similarly, like you think about in the spin thing, we talked a lot about constellations. You know, the other week we talked about you know, how the constellations can be used in the context of the spin statistics theorem, all that stuff. Well, constellations are like, you know, prime numbers in a certain way, really basic thing that like almost like at any scale, you know, observers, you know, in this world are going to have some kind of, I mean, if they live in 3 dimensions, they got a sphere around them, they're talking about different directions. I mean, that's a really basic pattern that is going to come up, you know, whether the aliens write down, you know, x squared plus 2x plus 2 or whatever, or have some different representation is kind of besides the point, you know.
But, you know, the analogy I would make, we know that lower animals that we would consider dumb, like horses, for example, can count.
Yeah, man. You know, I'm like, you know, I'm over the anti, you know, animal prejudice. It's like, I mean, that's the great thing about living in this time when, you know, everyone's playing around with so many neural networks. You just see, you know, learning, it's ubiquitous. Life is ubiquitous. Everything's got ideas and beliefs about everything else.
Michael, I think that I agree with you. Animals are very smart, and that crows can count and all this. But I think that the example of horses counting was actually shown to be a hoax.
Dun, dun,
dun. Okay, but you agree that certain lower animals can have a mathematical ability. The point I was trying to make an analogy that what we consider advanced math could be the math of a crow to a higher intelligence. That our math is merely our limitation in describing the universe.
Yeah, I can get down with that. that it's like the way that we.
Hey guys, I would like to make a suggestion.
Mhm.
I would suggest that for the next hour, we just let Matt go ahead with the presentation that Matt had in mind originally. If you don't understand something, by all means, interrupt to ask for an explanation. But let's reserve all comments for at least 1 hour from now.
Yeah, we may get it. It's just this is such an interesting and deep topic that we could talk forever about it in a way. All right, I'll continue on here. So we iterate multiplication to get exponentiation. We get irrational numbers, complex numbers. If we, allow division by 0, we can wrap the plane up into a sphere, a Riemann sphere. It was at that time that we talked about Gödel's incompleteness theorems, building a little a little classical computer out of, rational numbers. We then went on, we tried to ascend to a higher plane by considering, well, what if we had a pile of complex numbers, which would be like, you could think of it as points on a plane or points on a sphere. You could think of those as roots of a polynomial, giving us yet a higher order idea of a pile of pebbles, an equation. And by the fundamental theorem of algebra, the unordered roots could be associated uniquely up to a complex number with a sequence of coefficients. And thinking about the solvability of equations, we arrived at group theory. Then in the next, meeting, we talked about how polynomials form a vector space, and we talked about this nice interpretation of finite degree polynomials as, quantum states, specifically the spin states of spin J particles, interpreting the roots of the polynomial of constellations on the sphere, each root carrying basically a quantum of angular momentum 1/2. But, vectors are only defined up to a set of basis vectors. Hermitian matrices, which correspond to observables of quantum mechanics, automatically provide such basis sets via their eigenvectors. So now we got matrices. Okay, matrices are the new number. They could be finite, infinite. Their multiplication rule isn't commutative, so they can furnish representations of symmetry groups. And in general, linear algebra gives us, a theory of generalized perspective switches. And part of the quantum thing is that, we can generalize our idea of a perspective from, just a translation or a rotation or something, to that of a experimental situation by which a state is filtered probabilistically into outcome states, the latter of which provide a complete basis for the Hilbert space of the state, So instead of, the axes being like X, Y, Z, the axes are like the spin's up or the spin's down when you measure it. And so there's this interplay between geometry and probability. Then we went on to consider matrices of matrices, tensors, from which so much of the quantum magic comes. They allow for entanglement, sums of, states in the tensor product are also in the tensor product. And when particles get entangled, there's more information in the whole than in the parts, which means that, no naive classical kind of reductionism can work in physics. And as a cool example of that, we saw that if we take 2J spin half states and consider permutation symmetric tensor product of them, that corresponds to a representation of the spin J state. So instead of using like our polynomials per se, we could use 2J spin halves. And there, the constellation from before is encoded kind of holographically in the entanglement between the spin halves. And this itself was foreshadowed in the kind of holistic relationship between the roots of a polynomial and its coefficients. We discussed the theory of Clebsch-Gordon coefficients, angular momentum conservation, the idea that a tensor product of a bunch of spins could be decomposed into separate sectors with different J values, turning the and of a tensor product into an or. We sort of talked about angular momentum conserving interactions as being the basis of spin networks a little bit, and how those vertices in loop quantum gravity could be interpreted as quantum polyhedra, or atoms of space. Then, more recently, we turned to the harmonic oscillator, which is a kind of twin to spin. Spin and the oscillator being, I would say, the simplest and arguably most fundamental quantum systems. Instead of interpreting the roots of a polynomial as living on the sphere, which is like the classical phase space of a rotating object, you can interpret the roots of the polynomial as living on the plane, interpreted as the classical phase space of the oscillator, the real axis being position, the imaginary axis being momentum. And we discussed, coherent states, coherent state quantization, and then eventually graduated to talking about second quantization, where we introduce a harmonic oscillator at each degree of freedom of a first quantized quantum system, and we get a theory of indistinguishable particles. And to, continuing the theme of like using spin as like the canonical example, we introduced two harmonic oscillators for up and down states of the spin half state. And we came up with a representation of spin where you can take any J value. You can have a superposition of 0, spin half, spin 1. And, this double oscillator construction can be seen as, a theory of, spin with variable J value. Or, if you consider the, position and like momentum operators of those two oscillators, we can think about it as like a theory of polarization. Or we can think about it like a quantum field in the sense that it's a theory of a variable number of indistinguishable spin half particles treated bosonically. And, we talked about how to extend this a little bit, bosonic quantization, fermionic quantization, a little bit the connection between spin and statistics. And, the point is that, all known particles or whatever are of this type, indistinguishable quanta of some quantum field. And it's kind of nice because we sort of come full circle, because we could think about, in some way, any measurement as being reducible to the measurement of some kind of number operator, counting the number of particles like in that state. And so we can think about, our pebbles from way back when being contextualized by, okay, these pebbles count the number of quanta in some mode of a quantum field. And it is conceptually nice because, the pebbles in the pile are treated indistinguishably, just like the part of the quanta of the field. Okay. So that's the recapitulation. So that's where we've gotten to, but the story isn't over yet, as we've been saying. So, when you work with relativistic quantum field theory, basic demand is that the vacuum state with no particles is Lorentz invariant. In other words, translated, rotated, boosted observers are all going to agree about the vacuum state on the idea of what is meant by a particle. This just directly leads to Wigner's classification scheme based on mass and spin. And the idea is, what we mean by a particle should be like invariant or the same, whether we rotate it or translate by it, see it moving at top speed. And, we define a thing, a particle, in terms of what we can do to it that leaves it the same as something left invariant under the different perspectives we might have on it. And in general, I mean, that's just sort of how we should think about things or objects in general. They are defined by, a bunch of perspectives which leave that thing invariant. Now, as I'm sure many of you know, relativistic quantum field theory is hard. There's many subtleties. Necessarily leads to a theory of multiple particles. You got to consider these interactions, Feynman diagrams, endless loops. I mean, this could be happening, this could be happening. There's infinities. You got to renormalize them. You got to think about, how the theory works at different scales. Maybe consider conformal field theories that are scale invariant. There's so much to say, but today I just want to focus on just this one specific point. That's what, what is one set of particles from one point of view may in fact be another set of particles from another point of view. So, the classic case is, as we've said, like the Unruh effect, where an inertial observer in the vacuum will measure 0 particles, and an accelerated observer will measure a non-zero number of particles. And we get there via a Bogoliubov transformation, which we'll talk about in more detail in a second, which was first actually sort of talked about in the context of condensed matter. It's interesting in that it can take a Hamiltonian quadratic in creation and annihilation operators and convert it into simple oscillator Hamiltonian. And we'll see how it can relate the perspectives of inertial and these constantly accelerated observers, like in a, but it can also be seen as describing kind of like in condensed matter, where like parts of one system can kind of group up and travel around as meta particles or quasi particles. In any case, what is one set of particles from one point of view can be another set from another point of view. And indeed, there's these interesting theorems like Hogg's theorem, which in the case of interacting quantum fields, it's not always going to be possible to kind of like separate out like, oh yeah, these are the oscillators for this or that. Imagine it like photons, electrons, so tightly intertwined and interacting that, ultimately they can't be treated as separate entities anymore. Okay, so let's take a little journey into this, what is a Bogoliubov transformation. So basically we have to talk a little bit about symplectic transformations, or what does symplectic mean? We talked about a little bit way back when we talked about the meaning of the complex inner product. The word is kind of a joke in a way. It's a translation into Greek of the Latin word complex. Symplectic geometry is related to the phase space of classical mechanics. There, things come in pairs. They always have a kind of position paired to a momentum, even if those things get, a little bit more abstract. So there's a similarity to complex numbers, which always have a real and an imaginary part. And we've even seen in the case of like the oscillator how, we can interpret literally the complex plane as being like symplectic, position momentum plane of the classical oscillator. So the idea is that, symplectic or canonical transformations are going to transform positions and momenta among themselves so that you end up with another set of positions and momenta that precisely preserves like the duality between position and momentum. So just to be like really concrete about it, we can sort of consider finite linear symplectic transformations. And these are going to correspond to like, they're going to be even dimensional matrices called symplectic matrices. And it's got to be even because, we got P's and Q's that are paired up. So it's always going to be an even number of dimensions. So we can generate, here's like a little algorithm for generating a random 2n by 2n symplectic matrix. Okay. You generate 4 random real n by n matrices. And then you tensor each one respectively with the identity with I times Pauli X, I times Pauli Y, I times Pauli Z. And you add up those 4 terms, and then you do the QR decomposition into a unitary matrix Q times an upper triangular matrix R, and then Q is the desired symplectic matrix. It works because this matrix is going to preserve the so-called symplectic form. So if we take the symplectic form omega, in this case to be this, you can, there's different ways of choosing exactly how you represent the symplectic form, but suppose we've
what is a symplectic form?
Yeah, what is a symplectic form? It's just basic, it's just think about it like it's like a kind of metric that's being preserved. So
preserved under what?
So here's how I would like say it. Suppose you have like in quantum mechanics, you had like a vector of like a bunch of position operators, momentum operator, position operator, momentum operator. You can think about this, getting this matrix omega by interpreting each of these components as like the trace of, you know, the ith and the jth operator. And, you know, if you take the trace, or say, trace of the commutator. So, you know, if we take the commutator, you know, between Q0 and P0, you know, it's going to be I, you know, by the canonical commutation relations, times I gives you -1. And then if you do, you know, P0 commutator with Q0, the reverse, then you get the same with the minus sign. And so you can see that this is actually just encoding the commutators between the P's and the Q's. So then if we transform this vector of P's and Q's using a symplectic matrix that preserves this form, it's going to preserve the Heisenberg uncertainty relation, basically, between the different P's and Q's.
Can't you expand that and say symplectic form is a manifold?
It's, yeah, you can have the symplectic manifold. Yeah, it's, yes, yes. There's all this subtlety about symplectic spaces in terms of, you know, whether you should define a metric on them and other things. You know, it's sort of like, it's easier to find a notion of area. Area is more fundamental in symplectic spaces than the metric property.
And also, would a symplectic space necessarily be continuous or not necessarily?
Oh yeah, could it? Yeah, maybe it could be continuous. I don't know. Yeah, I guess so.
I mean, if it's a manifold, it would be continuous.
Yeah, yeah. I'm not. That's a good. It's an interesting question. Yeah, I don't know. I'm not entirely an expert in this domain, but I know this much. Here's some code. You know, if you're interested, it just implements this algorithm here. Generate 4, you know, random n by n matrices, tensor them with these little kind of, you know, you can think about these like in terms of quaternions. It's kind of interesting. We build up our little omega, and, you know, we test that this matrix omega preserves the symplectic form. And it gives us true. You know, you can see what it looks like, I guess. Huh, not that interesting to look at, but so, you know, right. So basically, as I say, you can think about these symplectic transformations as being like the general kind of transformations that takes a bunch of P's and Q's, combines them up, stirs them up in a big soup, spits out another set of P's and Q's, so that the P's and the Q's before, you know, satisfied the commutation relationship. Commutator of Q and P is I. And on the other side, the new P's and new Q's, they also satisfy that same relationship. So you could imagine transforming, however, you know, not the P's and the Q's, but instead the creation and annihilation operators, which, as we know, are, you know, linear combinations of the P's and the Q's. So like in that context, we can call the transformations basically Bogoliubov transformations. That's basically the difference. For a long time, I was confused about like, okay, what's the difference between like a straight up symplectic transformation and a Bogoliubov transformation? And this is basically the idea that these guys act on the creation and annihilation operators instead of the P's and the Q's.
What is a quadratic Hamiltonian?
So it's going to involve, you know, basically only like powers of 2, you know, so you could have combinations of creation and annihilation operators.
So it could be like the Klein-Gordon equation, for example? But then what happens when you get into, you know, lambda?
No, well, no, because you know, from a particular perspective, right? Like normally, you know, when you think about the Klein-Gordon equation, like when you solve it all out, like in general with the quantum field, like, you know, you get that you can like write the Hamiltonian as like a sum over just the number operators of like all the oscillators and stuff.
But it's no more than quadratic.
Sure, sure.
But then when you get into, you know, like symmetry breaking, for example, you might have to go to lambda 3 or lambda 4. So can bugaboo, I can't pronounce it, but bugaboo transformation. Does that work in symmetry breaking and, you know, higher? Apparently not.
It's an interesting question.
I know it's used to derive the Unruh effect. That's all I know.
Here, I just wanted to find like I'm just randomly like looking for like an interesting example of like.
Yeah, I'm just curious what they mean by a quadratic Hamiltonian.
Yeah, just that like you know you wouldn't have more than, you know, like 3 creation and annihilation operators multiplied together in it.
Oh. Okay.
So, you know, one of the simplest Bogoliubov transformations is the single mode squeezing operator. This is what they call it usually in quantum optics. So, you know, you can parameterize it by like some number R. It's got some hyperbolic sines and cosines in here. It acts on, you know, annihilator, creation operator, and gives you another pair of creation and annihilation operators. So, you know, if you multiply it out, you just get that little relationship. Now, in this case, you know, this same transformation, you know, which is like a little matrix, like acting on a vector of, you know, creation and annihilation operators, you could also implement this transformation with just like an operator known as the single mode squeezing operator, which you could write as e to the r, where r is this parameter, the annihilator squared minus the creation operator squared over 2. And, you know, you could, and in general, you could have a complex parameter z. So, you know, instead of using this little guy to transform this vector, instead I could sort of get the same effect by, you know, transforming A and A dagger using this operator, you know, by sticking it in between this and its adjoint. And it's useful to use this though, because then this guy has a more obvious way of like acting on states. So suppose I start in the vacuum state and then I apply the single mode squeezing operator. I'll end up in the so-called squeezed vacuum, which...
One moment, I'm confused. What does squeezed mean? Why do you call it a squeezing operator? Why squeezed vacuum? What is being squeezed here?
Yeah, so here, I'll show you a little visualization. So
this is getting too prurient for me. Squeezing?
Squeeze. So this is just, okay. So, right, so like I'm saying, you can parameterize the squeezed vacuum states, the single mode squeezed vacuum states, with just a complex number. So we see this from before. Here's an oscillator. And before we use this little thing, I could drag this point around to look at all the different coherent states. In fact, let's just do that first, just to remind ourselves what that looked like. So, you know, here we are. This is like the vacuum state. And I can drag this around and I can get all of the coherent states of the oscillator. And we see that, you know, dragging this guy horizontally corresponds to just translating the position of this guy. In other words, this plane can be interpreted as, you know, the real axis is like position of the oscillator. And then if I drag the guy, you know, vertically, you can see that the imaginary axis corresponds to, you know, you get all these little guys winding around there, corresponds to changing the momentum of the guy.
What are the purple circles?
Ah, yes. Well, the purple circles are the roots of the polynomial corresponding to the state. So they're like the stars, like in the spin case, but here, these are like they're on the plane. So in the coherent state basis or whatever of the oscillator, these points have like 0 amplitude. And they kind of make this cool like ellipse. Why an ellipse? Have to think about that. Now, and they make a cool pattern, as you'll see when we look at these squeezed coherent states. So let's look at that now. So what do the squeezed coherent states look like? Again, what we're basically doing is I'm dragging around this point, and it's gonna basically correspond to this complex number Z. And I form this single mode squeezing operator, and then I apply it to the vacuum state, and we like look at it. So whoa, oh my God, sorry. Can I just do this? I'll just zoom out without this freaking out? Okay. Haha, look at that. Kind of cool looking. So.
I don't quite follow what's
Yeah.
going on.
So the squeezed vacuum it's not a vacuum anymore. Like it's got particles in it is kind of the point. So the expected value of the oscillator of the number of quanta in the oscillator is now like non-zero. Yeah, what is the meaning of like the different, of like the complex plane in this case? Well, I don't know exactly what to say, but we'll see that when we consider the two-mode squeezing operator. We can, well, maybe I should just say that for a moment. So when we get to the two-mode squeezing operator, we'll see that the squeezing parameter depends on the acceleration of the observer, like in the Unruh effect. So that gives you some intuition. Let's see, Wikipedia had a little thing here, squeezed coherent state. That's a nice interest. Okay, the circle denoting the uncertainty of a coherent state has been squeezed to an ellipse with the same area. Well, that makes sense, right? If you recall, in the coherent state picture of the oscillator, if we had like a coherent state, and then we looked at what happened to it, what happens to it under the oscillator Hamiltonian, it made a perfect circle in the complex plane, in the position momentum plane, just going around so that the oscillatory motion of the particle or whatever turns into just this circular motion in the phase space. And so the idea is that the squeeze state it's doing the same thing, but instead it's making an ellipsoid in that plane instead of the circle. And it's an ellipse with the same area. That's one way of thinking about it.
But the squeezing doesn't happen along the X or along the momentum axes necessarily. It could happen in any direction?
Yes, and I suppose that's what this parameter Z is parameterizing. Yeah, actually, I should have looked at this a little bit more. I wonder if we can, can I do this?
Why do people bother with this? Before, with a coherent state, we have a nice circle. This is very simple. Why squeeze it into an ellipse? Why bother with it?
Well, we shall see, I suppose.
Okay.
Would this be like a transformation to Rindler coordinates or Kruskal coordinates?
Yes, we'll see that something like that's going to come up. Yeah, exactly.
Yeah. So, I mean, to answer Moshe's question, in order to describe a phenomenon like the Unruh radiation, you would need this.
Let me just, yeah, quickly, let's just take a look at this. Oh boy, sorry, I'm doing this on the fly. Can I, let me just do this really quick. Squeeze, coherent. Let's just see, I just want to see this ellipse thing. Is this really true? It's really true, guys. There it is. There you see it. So, okay, wait, so just undoing what I just did. Do. Oh, I didn't even need to do that. So, okay. Let's look at like a random coherent state of the oscillator. We see that its evolution in the complex momentum plane is just given by this circular motion here. This is just going around in a perfect circle. But if we consider, a random squeezed coherent state, it's well, that's not very squeezed. Let's do another one. Oh, I didn't do it, sorry. If we do a random squeezed guy, yeah, I mean, that one's not that squished either, but yeah, it is a little squished. You see, it's wider than it is tall. Let's do another one, maybe it'll be more clear. Yeah, look at that, that's a nice looking ellipse right there. Okay, so that's one way of thinking about the squeeze coherent state.
It seems that instead of having a uniform phase, you have a varying phase. Those vectors going around represent the phase.
Well, they're like the amplitude or whatever.
Well, they're the phase.
For the thing to be in the coherent state associated with that point on the plane. So like, these arrows down here on this line, they represent the amplitudes for the particle to be at a certain position on like the line itself. These guys represent basically the amplitude for the state to be at a particular, point on this plane. In other words, each one of these is associated with the coherent state at that point. Cool. So, you can see, so like just an even, no visualization here, but, okay, we create a little oscillator, choose some random value for R, we form the squeezing operator, and then we evolve the, we sort of transform the creation and annihilation operators with the squeezed guy. We, apply it to the squeezed vacuum. And And, you know, you can see that like the number operator, the original number operator on the vacuum, of course, gives 0 expected quanta. But this transformed number operator gives a non-zero expectation value on the same state. Similarly, if we look at the squeezed vacuum, then the squeezed number operator measures, you know, 0 particles, but the original number operator on the squeezed vacuum measures some, or particles, or quanta, or whatever. You can then consider two-mode squeezing.
One moment, Matt.
Yes.
Would it be fair to say that the operation that you showed us before, the squeezing operation with the hyperbolic functions, is this something related to a Lorentz boost?
Well, I guess I want to say, well, maybe in some sense, but I want to say no. I mean, we'll see that it actually relates to the acceleration parameter, like how much.
What parameter?
Acceleration.
Acceleration, okay.
Yeah, the Lorentz transformation only applies to inertial frames, but here you have an accelerated frame, so it wouldn't be a Lorentz boost.
Okay.
Can you get a squeezed coherent state from like a boost or something in some sense? Don't think so.
Could be a boost, but it's not a constant boost that you would have in, you know, Lorentz.
Well, I mean, you mean it is a constant boost. It is not a one-time boost.
Yeah,
it is a constant boost. So you continue boosting.
Yeah, that's what we're dealing with. So, you know, if we have two modes, you know, we have creation and annihilation operators for each mode, 0 and 1, let's say. And we can have this, you know, Bogoliubov transformation. Alternatively, we could write it similarly as—
One moment.
Mm-hmm.
Let me just look at it for a minute.
Sure.
When you had the previous Bogoliubov transformation, I thought you had the minus sign. Yeah, you had a few minus signs. And now I don't see, yeah.
Oh, yeah, you're right. Yeah, no minus sign.
Yeah, for the sinus hyperbolic, you had minus signs.
Yeah, I think that's right. If I'm correct, I'll double check on that, but I think that is correct. Could be wrong.
I don't say that you should have minus signs. I'm just a little bit puzzled.
Yeah, no, you're right. Yeah. Let's see. Two modes, squeeze state. Yeah, I might be off about it.
They're probably getting multiplied out.
Could be.
Yeah. Well, I'll double check for you on that.
Okay, for next time.
For next time.
Fair enough.
Yeah, and well, okay. So either way, you know, you can write the two-mode squeezing operator similarly as this like exponential, where, you know, A0 and A1 are the two annihilators, and these are the two creation operators of the two modes. And so you get a similar kind of effect, you know, basically disagreement about the vacuum. In other words, you know, on the squeezed vacuum, the number operators of the two oscillators is non-zero. and vice versa. And just for fun, I had like a little visualization. Where, you know, oops. This one's actually not, I don't think actually that like illuminating, but basically, so, you know, we still have this squeezing parameter and it's a complex number. So even though we have two modes, we can drag this guy around. Now, in this case, you know, the interpretation of what you're seeing is different than in the last simulation. In other words, we have two oscillators. And on the plane now, these are the amplitudes for the different positions on the plane, where like the one oscillator is like horizontal and the other one's like vertical. And we're dragging this around and we're looking at like the different squeezed vacuum states. So like before, the plane meant the position and momentum plane of like one oscillator. Here, we're dealing with two oscillators, and this plane is like the actual position plane of the two oscillators as like a two-dimensional oscillator. And we can see, you know, like here's a cool state, you know, it's kind of got this like X symmetry. These are the different, you know, squeezed two mode squeezed vacuums. If you just look at the these position expectation, or the position amplitudes for the two oscillators. And then just for fun, you know, somewhat irrelevantly, but, you know, just for fun, you know, if we have two oscillators, we could decompose it into a bunch of spins, you know, why not? So down here, you know, you see the different spins. And I didn't even expect this, but, and I'm not even sure why exactly, but only integer spins survive. All the half integer spins are gone. In the, you know, and all these different squeezed vacua, you know, this should be like 0, 1/2, 1, etc. And only the half ones are there. Like if we just, you know, choose some random state, that would, you know, would have components in all of them. Anyway, so there's that. Just a little.
Well, can I? You say only integer spins survive. So does that mean the radiation has to be photonic?
No, I just, well, I don't know if there's like a direct physical interpretation of what I just did. Like, you know, what we're gonna, in the context of the Unruh effect, you know, those two oscillators are counting, you know, the number of particles of like some scalar field of a certain mode. And then you.
But in the context of the Unruh effect, is the radiation just radiative? Is it just photonic, or can it be fermionic?
Yeah, it can be, yeah, all of the above. So, you know, we'll discuss it in the case of a scalar field, and it's just basically like you're getting excitations of that field. And, you know, you can do it in different numbers of dimensions, you know, fermions, with bosons, you know, more complicated fields and so forth. So, all right, so now we know about, you know, symplectic transformations, Bogoliubov transformations, single mode and two mode squeezing operators, and this idea of a squeezed vacuum. And so now let's just apply it in really very simple and to some extent hand wavy way to the Unruh effect. So, you know, basically the idea is that the Unruh observer who's constantly accelerating is going to see the Minkowski vacuum of the inertial observer as the squeezed vacuum, as like a two-mode squeezed vacuum. And the two modes are going to live in one of these two wedges of so-called Rindler space. So, you know, here's the trajectory of like a little accelerated guy. He's, you know, confined to this one region here. There's this two region. And when this guy's perspective, what he's going to basically see is a squeeze state sort of with like entanglement between a mode in 1 and a mode in 2. Although of course he's not going to be able to, he just keeps on accelerating. He's never going to be able to confirm that he really was entangled, but so it goes. So, you consider, say, this is just like very simple example, real massless scalar quantum field in 1+1 dimensions. Its modes correspond to solutions of the Klein-Gordon equation, just in 1+1 dimensions here. Nothing too tricky. You can write down, okay, so for like a given momentum mode in like Minkowski coordinates, you're gonna get this kind of thing. A little function of x and t, a little exponential. And, you can see that, this is definitely like a massless particle. Okay. So like in those terms, the energy operator is just that, you got a boost operator you can write down as this little differential operator. Okay. You could also adopt Rindler coordinates, where A is like the acceleration of like this guy. He's just constantly accelerating forever. And, the relationship between the Minkowski coordinates and the Rindler coordinates is just Minkowski t and x are just, have to do with the hyperbolic sine and cosine or whatever of the Rindler coordinates, which here are tau and chi. And you can see that they depend on A, the acceleration.
Matt, what do the 2 quadrants represent? Could you scroll back?
So, if this guy's coming in and he's constantly accelerating,
Right.
then, this quadrant basically represents like a kind of horizon to this guy's experience.
Right. But what about number 2?
Yeah, number 2 is, number 2 is number 2. Number 2 is over there.
What does that represent? I mean, who's in number 2?
Yeah, it's like, yeah, exactly. Well, I mean, basically, if there was another guy who was doing kind of the inverse thing to this guy, who was like accelerating over here like this, and then this guy, as he's going along, like measured one of these unrow modes and got like, oh yeah, 1 particle or whatever, then due to the entanglement, this guy would get some correlated answer.
Is the other guy accelerating?
Yeah, the other guy would be, like accelerating in just the same way.
Can we read what's at the bottom of
Oh yeah.
Rindless regions 1 and 2 are causally disconnected? So why does 2 necessarily have to be accelerating? I mean, 1 and 2 are entangled.
Yes.
But
yes.
they're not causal. So
yeah, and like that's kind of the cool thing, right? So it's like conceptually, like the way that I think it's worth thinking about it is that like by accelerating, it's like you're sort of trading spatial connectivity for entanglement. So like by accelerating, this guy basically like gives up, access to what's going on over here. But as a consolation prize, the states of the field in 1 are like entangled with those in 2.
But does the guy in 2 have to be accelerating? Why can't he be?
Well, to measure, to measure those modes, he or she would have to be accelerating as well. Because otherwise it's just the Minkowski vacuum. So we can adopt Rindler coordinates, and you can write out like what the boost operator and the Hamiltonian would be, and you can see that the Hamiltonian is just given by the boost operator. In other words, that's exactly what we were saying before, right? That it's like what to be at a constant acceleration is it's just you're constantly boosting. But as we've been saying, there's like 2 coordinate patches 1 and 2, these wedges. So we can also have coordinates like tau and chi prime. There's this little negative sign here. So then we can consider 2 Rindler modes, 1 in each patch. So for like, the momentum is K, and here's a mode in the patch 1, here's one in patch 2. And, this involves chi and tau, this involves chi prime and tau prime, and you see there's like a little negative sign here. Okay. So then let's consider the creation and annihilation operators of those 2 modes.
Can I ask why we're using, spin 0? The only spin 0 particle we know of is the Higgs boson, right?
Yeah, I mean,
because it's simple.
it's just
It's
simpler.
the simplest one.
So this can be very easily transferred to Dirac and Proca and whatever.
Oh, yeah. Mm-hmm. Yeah, you can find, many references will sort of lay it out. This is just sort of like the simplest possible way of doing it. So we got these creation and annihilation operators for these 2 modes. One is in the one Rindler wedge, one is in the other. This observer is moving with acceleration A, okay. So then we formed the 2 mode squeezing operator formed from those creation and annihilation operators for those 2 modes, where the squeezing parameter is something like arctan, whatever. It depends on the, mode, the momentum mode, and it depends on the acceleration. So then we have it that suppose this is the Rindler vacuum. So 0 particles on the left, 0 particles on the right. We apply the squeezing operator to the Rindler vacuum. And what we get, the idea is that what we get is the Minkowski vacuum. So that the Minkowski vacuum seen in Rindler coordinates or from an accelerated reference point is in fact a 2-mode squeezed state between the 2 halves of the Rindler space. What is the Minkowski vacuum for the inertial observer is an entangled state across 1 and 2, with particles. And in any case, as we know, this guy is like confined to region 1. And so not only is like the scalar field like entangled across 1 and 2, but the observer in 1 has to partial trace over 2 because they're, disconnected from it. And so, he gets like some density matrix. And it's kind of interesting. It's like as if by accelerating, the observer has traded spatial connectivity for entanglement. So, this is just, and I'm eliding over a lot of stuff. Like in a more thorough treatment, we would talk about, there's really 3 things you have to relate. The, Minkowski modes, there's the Rindler modes, and then there's also the so-called Unruh modes. The idea being that like these are just useful modes which share the same vacuum as the Minkowski modes, but which are supported on the left and on the right. And so, really you should talk about those. And there's some other stuff, I'm just sweeping under the rug, but just, for the sake of simplicity. So we just create, we get some creation and annihilation operators for 1 and 2, and we look at the Rindler vacuum. We choose an acceleration and a momentum. We get this parameter R. We form the 2-mode squeezer, and then we apply it to the Rindler vacuum, and we get the Minkowski vacuum. We then take just, say like an annihilation operator, and then transform it with that same squeezing operator in order to get say like a number operator for like Minkowski modes. Again, there's this like footnote about the Unruh modes, such that on this 2-mode squeeze state, this number operator is gonna be expectation value 0. So, okay, I just chose some random values for momentum and acceleration. We can see, okay, so the number operator for the mode in region 1 and region 2 on the Rindler vacuum is 0. Right, that makes sense. It's the Rindler vacuum. But if we look at say, like here, well, okay, you know, there's a completely reciprocal relationship. So, you know, on the Rindler vacuum, the number operators for 1 and 2 measure no particles, but the Minkowski number operator on the Rindler vacuum would be like, oh, there's some particles. Conversely, if you have the Rindler number operators on the Minkowski vacuum, they measure some particles, but the number operator on the Minkowski vacuum does not. So this is the case, the classic case of the Unruh effect, basically here, right? We have a number operator that on the Minkowski vacuum is 0, but on that same state, there's a number operator that acts on 1 and a number operator that acts on 2. And in fact, they show a non-zero number of particles. And if we take, you know, like the partial trace of the 2 halves, we can look at the entanglement entropy of these density matrices. It's like way non-zero. They're entangled. So there you go. So, you know, similar arguments lead to the Hawking radiation. So, you know, in the Unruh case, the idea is that, you know, an inertial observer observes no particles, but an accelerated observer would. And the 2 disconnected halves of Rindler space are entangled. In the Hawking case, you know, there's like some observer, you know, far from the black hole, and they are the ones who observes particles popping out of the curved space-time, which are entangled across the event horizon of the black hole, which eventually causes the black hole to radiate. So, you know, the 2 Rindler wedges, you know, like in the Unruh case, you know, are like sort of like left and right. In the Hawking case, it's basically inside and outside.
Can I ask a question?
Yeah.
Could you scroll down to the paragraph before this one? It says, if the accelerated observer were to measure a particle, this would naturally disentangle the 2 halves, leading to the appearance of particles from the inertial perspective.
Yeah.
What does that mean? If the accelerated observer measures the particle, then it also appears in the Minkowski space?
Well, not like exactly the same particle, but yeah, that's the idea. So that, like, right, like if the Minkowski vacuum seen from the Rindler perspective is this like entangled state between left and right. And then someone in one of those wedges makes a measurement. I mean, what happens when you make the measurement? But, you know, it's gonna collapse that and it's gonna break the entanglement between left and right. And so when you go back and look at what is going on with the inertial observer, it's not in the vacuum anymore.
But wait a minute. Let's say do you necessarily have to have entangled states between quadrants 1 and 2? I mean, what if you just
in this case, yes. So it's like that's the idea. It's like.
But what if you just have an accelerating spaceship, and the guy in the spaceship measures particles? Does that mean that the stationary observer also sees particles? No.
Yeah, at that point, yeah, they would see some stuff happening.
But only if he measures it.
Yeah, yeah. If it, you know, by measuring it, you're disentangling the modes across left and right, and a disentangled state across left and right is going to correspond to, you know, not the vacuum state.
And there always is entanglement between left and right. You can't just have a right without a left.
It seems not. It seems like this is how to do it. Yeah.
So what's the whole point of Unruh radiation? In order to have it, it's got to be measured by the accelerating observer, and once he does that, The stationary observer sees particles too. I
So, yeah.
I don't understand.
Okay, my understanding of what's going on is the following. If you have an accelerating observer, the accelerating observer has an antenna and he sees stuff using his antenna. He has a detector, he detects things. The stationary observer is going to see radiation being emitted by the accelerating guy. He will see the accelerating antenna is emitting particles.
Okay.
Basically,
So, yeah, can you look at it that way?
basically, if you have an accelerating conductor, you have electromagnetic radiation coming out of it.
Yeah, that's a nice picture. Yeah, I mean, that, you know,
But
one thing I
let's say
I
you
feel like
don't
I
have
need
an
to-
antenna. Let's say you don't have an antenna. Let's just say you have a spaceship that's made out of plastic and it's accelerating. Can the stationary observer see particles? I thought the whole point is that the stationary observer does not see particles.
Well, if the accelerating observer is made not out of plastic, but if it's made out of dark matter, it is quite possible that the stationary observer will not see anything at all.
Mm.
But how does that jibe with what Matt just told us?
Well, if the accelerating observer is made out of dark matter, he doesn't have any antenna, he cannot detect anything.
No, but let's say
Yeah, I could see.
dark. Well, first of all, again, I don't believe in dark matter. Let's say forget about dark matter. Let's talk about real particles.
Yeah, I mean, I need to understand better, you know, and this is like failure on my part. Like, I need to understand better, like exactly, you know, how these things fit, these different perspectives fit together. So, like, I mean, I think it's certainly true that there's a sort of complementarity, right? It's like, if, you know, you're in the Minkowski vacuum, inertial observer measures no particles, but an accelerated observer would see some particles. But if they measure those particles, they break the entanglement between left and right, leading to the appearance of particles from the Minkowski perspective.
How do they see the particles without measuring them? They've got to.
No, I mean, that's what I mean. If they measure it, you
They've
know?
got to have a measuring device,
Yeah, of course.
or else they don't know that there are particles there.
Yeah.
So what are we talking about?
So I'm talking about, it's right. So like the accelerated observer makes a measurement of their mode. And then, you know, if the inertial observer, there's going to be some mode that he can measure or whatever, that's going to be non-zero. Precisely.
So it looks like they both see particles. It looks like
Well, that's what I mean. So like if the accelerated observer does not make a measurement, then yeah, the Minkowski vacuum is just Minkowski vacuum. But if they do fuck around with their modes.
But if he doesn't, but if the accelerated observer doesn't make a measurement, how does he know there are particles there? He's got to make a measurement to know whether.
I mean, I'm not. Yeah.
There's got to be a particle detector.
One moment, there's a bit of confusion here. It doesn't matter if the observer makes a measurement or not. You have something, it is just a blob of whatever that is accelerating. The accelerating blob of whatever is going to detect particles. Maybe it will detect electromagnetic radiation, maybe it will detect baryon, maybe it will detect mesons, it will detect stuff. And the stationary observer will see the blob, the accelerating blob, as emitting stuff.
Yeah, like the thing that I wish I understood more about was like, okay,
Does
suppose.
the amount of stuff depend on the mass of this accelerating object?
It depends mostly on the acceleration.
I don't know what the difference is between creating stuff and seeing stuff. I mean, you gotta measure it. You've got to have a particle detector on the ship to measure particles. What you're telling me is that once you measure particles, then the stationary observer sees them too. That's not what I thought the Unruh effect was all about.
Yeah, I mean, I am saying that, but of course, you know, to say like, oh, they see them too, you know, what do you mean by them? It's like the thing that I wish I understood more about is exactly like, suppose the accelerated observer measures a particular mode, you know, yeah, like exactly how does that manifest for the inertial observer? Like, you know,
Okay,
like
the way
which
Sean
modes are
Cowell
excited for them?
the way Sean Cowell explains it is the following. You have an accelerating blob. It doesn't matter if you have an observer there or whatever. You have an accelerating blob of whatever.
Mhm.
The accelerating blob will be emitting particles that will be seen by the stationary observer. The stationary observer will observe radiation being emitted but by the stuff that is accelerating. Every time the stuff that is accelerating is emitting a particle, it will see it as detecting the corresponding antiparticle. It will detect the recoil reaction to the emission. So if it emits an electron, it will say, aha, I just detected a positron. If it emits an antiproton, it will say, aha, I just detected the proton. So basically, the radiation being seen by the accelerating observer is the recoil reaction of what the accelerator is emitting.
So then is their respective vacuum energies different? The point is that the stationary observer sees a zero vacuum energy, I thought.
As
Whereas,
long as there's no accelerating object, if it is a true vacuum, absolutely true vacuum, then the stationary observer sees nothing. If it is a true vacuum plus an accelerating blob, then the stationary observer will see radiation.
so the two vacuums are equivalent then. The Minkowski vacuum and the accelerated vacuum are equivalent.
Yeah,
Really?
Well,
well, you can say it in the following way. You start with a Minkowski vacuum. You have a stationary observer in a Minkowski vacuum. There's absolutely nothing there. Now you put an accelerating observer in the Minkowski vacuum. The accelerating observer is going to detect UNO radiation. But if you have an accelerating observer in the Minkowski vacuum, it is no longer a Minkowski vacuum. A Minkowski vacuum does not have anything accelerating within it.
Yeah. See, a lot of the explanations are wrong. I've seen a lot of explanations that say the Minkowski vacuum is zero, and
Yeah, it is
whereas
zero.
the accelerated, but not once you have an accelerating object.
Yeah, then it is not longer a vacuum.
But that's not always the way it's been explained. Yeah,
well, again, you know, I mean, you can be, yeah, there's interesting interplay between, as you say, Moshe, between, you know, the matter and the antimatter. It's interesting, yeah, because, you know, like from what I just said, like you wouldn't have necessarily guessed that, you know, the Minkowski observer would see, you know, radiation or particles or whatever coming from the accelerated observer.
apparently you see antiparticles coming from there.
Well, you see the exact opposite, the complementary of what the accelerating observer sees. Again, because what the accelerating observer claims to have detected, he just detects the recoil reaction of whatever it is that his antenna is transmitting. His antenna is emitting a proton, the recoil is going to be, aha, I've just detected an antiproton. This is the recoil reaction of emitting a proton. Now, in order to emit a
Well, 'cause,
proton,
like, in
you
this case,
need to have a huge acceleration. And when you have the huge acceleration, you emit a proton, but at the same time you say, aha, I just detected an antiproton.
So here's the thing, is there a
Well,
minimum?
in this case, though, I mean, at least, I mean, there might be.
Remember what I told you before, that
Yeah.
there is a general auditor that makes sure that the books are balanced. The books are going to be balanced.
So Moshe, if there's
theoretically
two of these guys, if these
What?
two of these guys sitting next to each other, do they, riding next to each other, do they emit two protons in that case?
Independently of each other, yes.
And so it does depend on the mass.
Ha.
I don't understand, Andre.
Look, if you
Can
had,
you repeat your question?
so it depends on the mass. Because if you had two of them sitting next to each other, but if you had three of them, then, so, and if they're all holding hands, then they don't, because they're holding hands, don't all of a sudden emit one. It's just like two guys jumping off the Tower of Pisa. If they're holding hands, doesn't change their acceleration. So here you have something that emits a proton, you have another one emits a proton, and then they hold hands. So now they're two, they're twice the mass, so they got to emit twice the stuff.
Sure.
And here's another question. You know, particles are quantized. You can't have an infinitesimally mass particle. There's a minimum amount of mass or energy you need to create a particle. So doesn't that mean that you have to have a certain minimal acceleration to emit a particle? So you would need a huge acceleration. What's
Yeah,
your
you
understanding?
definitely need, that's true, you need to use huge acceleration. Let's look very carefully at what we see right now on the screen, at the bottom paragraph, the expression that gives you the temperature. You see that the temperature is proportional to the acceleration.
Right.
I do not see the mass of the observer coming into play here. The temperature depends only on the acceleration, and that's it.
No, but you need a minimum energy to create a particle. Particles
That's
are
right.
quantized. So you would
right.
you would need a huge.
The energy comes.
Yeah.
Yeah, that's right. And the energy comes from the acceleration. In order to accelerate, you have to put in energy.
Okay.
Acceleration doesn't come for free.
So if you are not accelerating by at least a certain minimal amount, you will not be creating particles, because you can't create.
Exactly. Exactly.
And in the
That's
real,
exactly what this relation tells you. The temperature is proportional to the acceleration.
so in the real
The
world,
temperature
probably
is,
could not create particles.
okay, the temperature is the energy. Temperature is energy.
Yes.
If you are going to create a proton with mass, this corresponds to a huge temperature. A huge temperature will correspond to a huge acceleration because they're proportional.
Right.
So you will need a huge acceleration in order to create protons.
And of course, you cannot exceed the speed of light. So you would have to accelerate so rapidly to create a proton, or even a photon, or
Yeah,
even a
this is
photon. So
why
in the real universe, it may not even be possible.
Yeah, this is why it's been so difficult to measure the effect. Because yeah, for like the accelerations we have access to, it's a very tiny effect.
Exactly. Exactly.
So
Now,
many,
you have to be very careful. You can have a huge constant acceleration forever and ever, and you will never reach the speed of light.
How's
If
that?
you can go back, just let's go back to the initial picture that we had for the accelerating observer.
Yeah, he just like is asymptoting to this.
Exactly,
Right here,
that's
he
it.
never gets
Here,
there.
here, A is accelerating forever and ever with a constant acceleration. It never reaches the speed of light.
Why not?
It is asymptotic to the speed of light. It is asymptotic to the cone, to the light cone.
Yeah, and if you think about it, it's like
And basically
only mass
here,
that's
constant
particle.
acceleration means that you expend a constant amount of energy per unit time, and the real acceleration becomes smaller and smaller in a sense, because your mass goes to infinity. The effective mass of observer A goes to infinity by a factor gamma, 1 over square root of 1 minus v squared over c
So
squared.
how can the acceleration remain constant? It has to slow down.
So it's just like as you're continuing to accelerate, like your velocity is getting closer and closer to the speed of light ever more slowly.
I understand the force has to be maintained, but the acceleration has to diminish because of the increase of the mass.
That's right.
Approach the speed of light. So maybe
That's right.
so from the perspective of the accelerating observer, he's accelerating at constant acceleration, but from the perspective of a stationary observer, the acceleration is actually slowing down.
Well,
But now look at something very interesting. Just using this picture, look at A, and suppose you have this guy starting where this hyperbola crosses the x-axis. That's it. That's the starting point. And so here, A is at rest because the tangent is vertical. So A is at rest. And now A starts to accelerate with a constant acceleration following this hyperbola. Now look at a beam of light emitted just from the center, from the point x equals 0 t. Here you have a beam of light. This beam of light will never catch up with A.
Right.
Never.
Okay, but
even though A starts at rest, and A never reaches the speed of light, and the beam of light is always at the speed of light, it will never catch up with A.
Okay, but these Rindler coordinates are from the perspective of the accelerating observer. From the perspective of a stationary observer, the acceleration would slow down. Otherwise, you would exceed the speed of light from the perspective of a stationary observer.
Yeah.
So it's only from the perspective. It's only from the perspective of an accelerating observer that these Rindler coordinates are valid. In which case, he can assume the acceleration is constant. But in reality, from a stationary observer, he's slowing down.
Right. Yeah, because you'd be
getting exceed the speed of light.
Getting closer to the speed of light ever more slowly.
From the perspective of a stationary observer.
Okay. Okay. I can see that.
Could you go back to that temperature equation?
Oh, yeah.
So, I mean, what don't I understand here? To me, temperature is average kinetic energy.
Mm-hmm.
If A is 0, the average kinetic energy is 0. Just like what happens at absolute 0? At absolute 0, particles, a proton doesn't disappear. It just goes into its ground state. That's it. So these things aren't, this isn't creating particles. This is just creating the kinetic energy of the particles.
Yeah, but you're not going backwards, Andre. You're assuming that your temperature is constantly increasing to create particles. Once the particle is created, you're not going backwards in temperature.
I don't understand that sentence.
I mean, this temperature shows you.
Well, we've assumed that the acceleration is just some constant.
Yeah, it's got to be positive. The acceleration can't be 0. You wouldn't create a particle.
I'm saying, I'm going back to what you started, Michael. Look, you need a certain amount of energy to create the particle at rest. You still have 0 temperature. Then you need a certain amount of energy to get the particle moving.
No,
This
but you
equation,
don't create the particle until you have a sufficient amount of energy.
I'm
No,
saying, I'm saying T can't be proportional to A. I
no,
don't get
no. We have some confusion here.
Yes, obviously.
T is temperature. Temperature is energy. A
Temperature is
particle
not
at
energy.
rest has energy.
Temperature is kinetic energy. It's not total energy.
My understanding is that here T represents the total energy. I may be wrong, but that's my understanding. That's the only way I can understand it. If you tell me that in this expression, T for a proton at rest is 0, then I do not understand this relation at all. If you tell me that T is the total energy of whatever it is that's being created, then okay, then I understand it. Then it makes sense.
That's just not what temperature is. That's just not what temperature is. Look, I'm reading the word temperature.
All right, look, I can answer you. The energy is kT. If you multiply both sides of this equation by K, kT is energy, and then the energy would be HA over 2 pi C.
KT is kinetic energy.
KT is energy.
No, yes.
So the energy would be HA over 2 pi C.
And when T is 0, particles don't disappear.
Well, no, but
protons don't disappear when their temperature goes to 0.
When T is 0, you don't create a particle. This has to do with at what temperature do you create a particle?
Or
the point is, what is a particle at rest? In whose reference frame is the particle at rest? Which observer sees the proton being at rest? A proton is being created. Who sees the proton at rest? If you talk about the accelerating observer, if the accelerating observer sees a proton at rest, and by the way, again, this observer is accelerating. Maybe it was the proton was at rest at the instant it had been detected. But since the observer is accelerating, then we have to be careful about it. But meanwhile, the proton that was, the antiproton that was emitted in this case, if it was emitted at rest in the frame of the accelerating observer, then it is not at rest in the frame of the stationary observer.
And you know, and
that just makes things more confusing. If there are two particles being created, now just because the baryon number is conserved doesn't mean the total energy is conserved. You still need energy. You still need 2 mc squared to create the two particles. And according to this, if the two particles were then created at rest just next to each other, which I don't see a reason why they can't be, then at what acceleration do you do that? At 0 acceleration?
Well, it's not saying that like all temperature is the result of acceleration. You know what I mean? Like you could be at rest.
That's right. We're saying the end. We're saying, so now we start off, there's nothing. There's the vacuum. Now I start accelerating. I can't create anything until I create, if I'm doing protons, maybe I'm doing photons. Photons can be as small as you want. But if I'm doing protons, I can't create anything until I get 2 mc squared. And when I get 2 mc squared, they're sitting there at rest, temperature 0.
Well, maybe the issue is, yeah, like trying to, you know, make this sort of jive with like this sort of notion of like particle creation. I mean, because if you look at like what this squeezing operator does. You know what I mean? It's like, like what is this saying? Like this is like the density matrix on the left side, and on the right side, this is a mode of a scalar field. And so this is saying, with like 60% chance, there's 0 particles in that mode. There's a 24% chance there's 1 particle in that mode. There's about a 7% chance there's 2 particles in that mode. And so, you end up, in some like superposition of like there being different numbers of particles. In fact, it's still most likely that there's 0 particles there. And
No, but going back.
so it's like, it's not like imagining it like, well, you're accelerating and there's amount of energy, and then like when it crosses a threshold, you get a particle. Maybe that's not the right way of looking at it.
Going back to the equation, I think to answer Andre, the equation is ass backwards. The equation should really tell you what the acceleration is. The acceleration should be 2 pi c kt over h bar.
Well, it's
What
really
acceleration?
like, anytime you see a temperature, you could like work backwards and be like, I must be accelerating with reference to some.
And the thing is, KT gives you the energy. The Boltzmann constant times temperature gives you the energy. You can replace that with energy, K sub BT. And then what acceleration do you need to give you that energy? Well, that formula, the other way around, will give you the acceleration you need to give you the energy to create a particular particle, or as Moshe said, particle and antiparticle. But if you're creating photons, which is probably the only thing you can create, it would require too much energy to create anything else, too much acceleration. If you're creating photons, what is the antiparticle of a photon?
Yeah, there's
it's also a photon.
Also a photon. Yeah,
photon
and in fact, in this example I gave here, I guess like this is like a real scalar field, massless scalar field. So like, this one doesn't have, like at least in this exposition here, this doesn't so much depend on, the one being matter and antimatter. Like you still get an effect.
Well, but the thing is, in practice, you're only going to be able to create photons. You're only going to be able to create photons, and the photon is the antiparticle of itself.
Yeah.
There's no problem.
Right. I just wanted to clarify because, I mean, Moshe's right. When I've read these things, it's like, there's this like interplay, when you're, running this analysis for like a fermion, like a Dirac field or something, et cetera, et cetera, et cetera. There's like, this interesting interplay between, matter and antimatter, and like positive energy and negative energy solutions.
But it's never going to create a fermion. I mean, the acceleration you would need over such a short period of time would be ridiculous to create a fermion. Photons are really the only things you can create. And, like Andre said, you could create a photon with a minimal amount of energy. It would be a very low frequency photon.
Okay, let's look again at the equation for the temperature that you see in front of us. Not the first one, but the second one. This is the temperature of a black hole. This is the Hawking temperature of a black hole, where it is proportional to the surface gravity. What this tells you is that the wavelength of the radiation is the size of the radius of the black hole.
Right.
If you have a big black hole, 1 billion solar masses, the wavelength is 3 billion kilometers. So it's that's why we can see it. We cannot see a photon with a wavelength of 3 billion kilometers. But if the black hole is very, very small, like a nanometer, then the wavelength is a nanometer. And if the wavelength is a nanometer, well, then you can have whatever particle you want. It doesn't have to be a photon.
No, but Moshe, to create a fermion, you need a minimal amount of energy. So the acceleration would have to be huge. With
That's
photons,
right.
Well,
That's
by the way-
right.
you can create the smallest energy photon you like. Of course, you wouldn't see it because it would be a huge wavelength. It wouldn't even be a radio wave. It would be so redshifted that you couldn't even detect it.
Okay, guys, I have to, as I said, I
Yeah,
have to
yeah.
go because the religious side of my family is calling me.
Okay.
Yeah, great talking to you, Andre.
Okay.
Thanks for coming.
Next week.
Happy New Year to your wife and your son.
Okay, thanks.
Yeah, Lashana Tova.
Shana Tova, and I'm looking forward to next week. So I'm really looking forward to continue this presentation, this discussion. It is really interesting. And
Moshe,
again,
you have to use the Ashkenazi pronunciation, not the Sephardic pronunciation. It's Lashana Tova. Accent gra,
okay.
accent agu on the first syllable.
And again, Matt, really appreciate.
Yeah, thanks for
Really
coming out.
appreciate this presentation and looking forward to the next one. That's great. And let me just repeat, Matt, what I said before. You should think about the possibility of getting an advanced degree in physics.
Oh,
I'm
yeah.
not telling you go sign up, but all I'm telling you is think about it.
Oh, yeah, don't worry.
Think about it.
Matt, you should follow in the footsteps. You should follow in the footsteps of Dyson. You know, Dyson, who was one of the greatest physicists of the 20th century, did not have an advanced degree.
Really?
Yeah. And did I tell you, I met him. He had the personality of a dish rag, but he must have been brilliant.
He must have been really. They kept him around.
But he didn't have an advanced degree, and yet he was still able to do what he did.
Yeah.
Now, Matt, if you do think about getting an advanced degree, I would be at a loss of suggesting what a degree. Should it be a master's because you don't have a master's? Should you go straight for a PhD? Because I think that you know most of the stuff that you need in order to go straight for a PhD. And you may want to look at the kind of a test that they give you when you want to go to grad school.
Yeah.
Just think about it.
No, I have been. You know, it's funny. It's you know, I bought a GRE physics, you know, study book over the summer, with the idea that, you know, if I do apply to a PhD program this fall or something, I should take that test. And then they canceled it because of COVID. No GREs this year. I don't know if that's good or bad for me.
Look, I know a Russian hacker who can get you a degree for a very small fee, but it's got to come through me. Very small, $100,000 down payment. Pay the balance and
That's cheap.
you're certified.
I don't think that Matt is going to need this kind of approach.
But he needs the sheepskin. He needs the paper.
Yeah, it helps.
Yeah, I got to get that paper.
Yeah, unfortunately. I mean, there are a lot of people who are smarter with self-study than they are with
Yeah.
formal education.
Yeah, I mean, I'm taking a class at, like, a grad class at Penn right now in, like, nanotechnology, just as like a
very good.
continuing education thing, you know, not part of the master's.
But is that what you're interested in? Are you interested in the engineering aspects of it?
Well, I mean, I like the professor. I took another one of his classes, and I mean, yeah, I mean, it's not something that I know that much about, like this, you know, specifically, you know, nano scale, nano boxes.
Yeah, but if you want to be a theoretical physicist, you don't want to, you know, take the engineering courses, you know.
Well, I was sort of sneaking in, you know, it's like they had a lot of prerequisites for the quantum classes, which I could probably do it, but like I didn't have it on paper. But I knew this professor, and like I was just able to get into this class. So, you know, just
What about Terrell? Are you friendly with Terrell? Does he have any advice?
Oh yeah, I could ask Terrell. You know, yeah, we should talk about it. I haven't seen him. He hasn't come in.
Terrell is very weak on physics. I attended one of the. I hope he's not listening. He's not
Cut this off
doing
and
that.
part off of the YouTube video.
But he's a quantum computing specialist. Do you know he didn't know he confused a photon and a proton? He kept
Hey,
saying,
yeah, from the fucking world of quantum computing, yeah, who gives a shit, you know? That's it's
but
from
I'm
a
saying he's weak
perspective,
on
it's kind of
physics. And by
depressing.
his own admission, he's weak on physics.
But I think that's progress. Like that's what progress looks like. In the same way that like I don't need to know how like the CPU and memory of this laptop works. I can just care about the software. Like that means we're evolving as a field where you could like do quantum computation and like never even heard of a gluon or a photon or any of that stuff. It's just software now.
Excuse me,
Now,
Matt.
by the way, Matt, one reason why I said that I'm not suggesting that you should go into physics. All I'm suggesting is look into it. The reason I'm not proposing that to anyone to go into physics is because before the pandemic, I used to go to NYU seminars at least once a week. And they have a whole bunch of absolutely brilliant postdocs there, each and every one of them. And there are not enough positions for each and every one of them.
Right.
I don't think that even one of them is on a track to become a professor.
And also, if you want to do particle physics, you can't do it in this country. They're closing down all the particle accelerators, the Tevatron, Brookhaven. You got to go to Europe or to China to do particle physics.
Well, there are lots of brilliant people here doing theoretical physics.
That's all you can do here. You can't do cutting edge physics in this country anymore. We are no longer a leader, thanks to the geniuses in government who make these financing decisions. They closed down the super
Trump too. I mean, they could have built that big collider back
The
in
super collider was closed down by a bunch of idiots who didn't understand the point of basic research. So now you got to go to CERN or probably to China to practice your profession if you're a
China in at least 10 years before you go to China.
well, you have to go to CERN, so you brush up on your French. Moshe can give you lessons in French.
Excuse me, Matt.
But
What's
yeah,
your background? You have a master's in mathematics?
I do not have a master's in math. I actually have a master's in creative writing.
Oh, really?
Yeah.
Okay.
But I've been programming computers, for
You know what you should do, Matt?
Okay.
The best recommendation, what you should do is run for president as a third-party candidate.
Yay!
But get your paperwork in by midnight tonight.
Oh, yeah, it'll be me and Kanye.
Yeah, Kanye can't qualify. He couldn't spell his name right. They disqualified his paperwork in most of the states, but you know how to spell, so.
Okay, guys, this is getting over my head already, so I will have to leave and see you guys next week.
Yeah, see you, Moshe. Thanks for coming.
Take care,
See you
Moshe.
tomorrow, Moshe. What kind of
Bye.
next week? Mañana.
Yeah, actually, I should probably go too. I have a little thing to get to in a little bit.
He's been doing quantum gravity. What he's going to be doing tomorrow, you probably know. He's doing gauge theory tomorrow. Barry is.
Right.
I'm not sure if he's going to explain why gravity is a gauge theory or is not a gauge theory, because there's a difference of opinion.
So I hear. Yeah.
Yeah, I mean, I believe it's a gauge theory. The math seems to be the same as diffeomorphism is
yeah,
a gauge
I forget
theory.
the argument for why it's why it doesn't qualify as like a Yang-Mills theory, but yeah, and especially like the loops people are often kind of emphasizing like the gauge aspect.
I mean,
Hopefully I can make it. I might be busy tomorrow, but I would like to go to that.
Yeah, but he if you look at the New York website, he he put up a couple of links to, I don't know if you know who David Tong is.
Yeah, yeah.
He's one of Barry's favorites. And David Tong has a whole series on a lot of things, but he put the one up for, gauge theory.
Nice.
It's like a course. It's a multi-part.
Yeah, I've seen
course.
over the years. Yeah, many PDFs of great stuff from Mr. Tong.
Yeah. All right. Well, thanks, Matt. Are we doing something next week or?
Yeah, hopefully, we'll be able to meet next week. I'll talk a little bit about the 3Qtrit error correcting code as just like a toy model holography. And talk a little bit about we'll return to like wormhole models, very simple wormhole models, like we talked about.
And do you believe in wormholes?
Well, yeah, I mean, there's good reason to believe it. I think that it's fair to say it's, no weirder than quantum teleportation, but just.
Well, quantum teleportation is a very specific thing in quantum computation. It can be done,
so
but you're not teleporting physical objects like they do in Star Trek.
Well,
you're teleporting quantum bits. And then you have to send the classical bit to enable it. So you're not really.
So like in the case of the wormholes, you have two entangled black holes, and then there's got to be a coupling between them.
But has anybody ever seen Alice jump into one and pop out the other? I don't know. My next door neighbor said he did see that, but he was very drunk at the time, so I don't know if it's valid.
Probably not.
Well, what it lets you see is, like this interplay between, we've seen today, for example, like there's this like 2-mode squeeze vacuum. There's this notion of like, one side and another side, they're entangled. In the wormhole case, it's like the two black holes are entangled. And what was I gonna say about it?
And has anybody ever seen entangled black holes? I mean, let's start there. And by the way, with wormholes, I think they've already proven that you can't keep the wormhole open long enough for a material object to get through.
There was Maldacena had a cool paper where he was, dealing with Maldacena, right? Maldacena.
Yeah, but I would put Maldacena in the same category, in the category of people who believe their own bullshit.
Traversable.
Yeah, so he's got this cool paper, humanly traversable wormholes.
Yeah, right.
There you go. But
like I said, my next door, that Alexei Malenkin, that's my next door neighbor, but he was very drunk when he saw this.
I think it's at the end of the day, like not interpreted in terms of quantum gravity. I mean, you're dealing with a situation of like scrambling information, getting like kind of delocalized over another quantum system. And then if the dynamics are right, that delocalized information can like relocalize somewhere else. But then of course, like when you think about it in the quantum gravity context and, involving like the equivalence principle and like whatever, then, there's this extra interpretation, right? That like, you can just fall into the black hole and then come out the other black hole. And so there's like a spatial connectivity. And like, I would say like, yeah, that's the part. Yeah, we don't know. We don't know exactly.
Well, see, that's the premise. That's the premise that I don't accept, that you can fall into a black hole. You can fall onto a black hole. Who's to say that you can fall through the quote event horizon, which I would just call the surface? Why is a black hole not just the way Laplace described it 200 years ago? It's just a solid object from which light cannot escape. Who's to say that it's empty space? I mean, who came up with this?
It's a gravitational phenomenon. But I mean, it's like what we've been saying, today, that like, it's that like stationary observer that, you're right, sees you like fall like onto the black hole.
No, but I'm saying, why is a black hole not a solid object? It's just a very dense solid object.
because it's a phenomenon that's like a gravitational one. It's like the curvature of space-time. And by like the equivalence principle, it's like, you know, you're just going to be, you know, it's like if you didn't know you were passing through the event horizon, like you just wouldn't know. I mean,
the curvature,
if the curvature is strong enough, you would experience, right, like tidal forces.
the curvature at the surface is not infinite. It's not a singularity. And this whole thing about the center being a singularity.
Yeah, through that, yeah, whatever. That, you know, that doesn't matter. Yeah.
The whole thing about the center being a singularity is a mathematical quirk.
Yeah, the interesting stuff happens on the horizon, for real.
Well, which I would call the surface. Why is it any different from the surface of any other celestial body?
Well, because, you know, again, you wouldn't know when you passed it. Right?
You wouldn't know what?
It's just empty space, right? Like you wouldn't know necessarily that you'd even crossed the event horizon. Like,
but who's to say that you could even penetrate the surface of a black hole? Where did that come from? Because Hawking decided after saying that a black hole was a dead object that had zero entropy, then he started doing quantum calculations and decided it was a quantum object.
Right.
But again, who's to say it is?
Because it's not an object per se, because it's built out of curvature. Like it's a geometrical thing.
But so is the Earth.
Well, in a different way.
So is the sun. Is there a singularity at the center of the Earth?
The Earth is all this matter, and then it's also curving space-time.
But why? That's my question. Why isn't a black hole just a lot of matter?
Yeah, why not? I agree.
I see what you mean, right? It's like, well, because, well, yeah, I mean, it's all the stuff that fell into it.
Fell onto it.
I'm not going to be able to give you like a knockdown argument for like why that's not the case. But yeah,
it's only when you do quantum calculations a la Hawking, and this was Hawking's second or third go round at it, because at first he believed that entropy is destroyed in a black hole. But then he decided, under pressure, I believe, from other physicists like Susskind, to treat it as a quantum object. And I think that's where he went wrong. I mean, and the empirical evidence, we have no
pressure from other physicists.
Solid object.
I just mean, you know, they're just natural contradictions, you know, that we're trying to be resolved.
What's the contradiction? You just have a lot of matter clumping together. And as you add more and more matter, it just gets larger and larger, and light cannot escape from it.
But again, I'm saying, like, okay, so just from what you're saying, right? It's like if the matter is all clumped together, you know, and it has a very, very strong gravitational field, it's like even still at the event horizon, tidal forces aside, like you wouldn't necessarily know that you were crossing it. Okay, you know, outside of like, what about the other crazy effects that happen around?
Who's to say that you cross it? You fall onto the surface. Like you would fall to Earth, you fall to the surface.
Yeah, it's like a neutron star or something.
Yeah, I mean, why is there this assumption that it's empty space? Why is it not a solid object? Which makes more sense.
Well, I guess the question is, yeah, like, I mean, given the gravitational forces, how much must all the matter be compressed down such that you like couldn't look at it like, you know, a bunch of matter just like hiding right inside the event horizon or whatever.
Yeah.
So how do you get that space-time curvature if the matter is destroyed? If there's no matter left.
No, I mean, I'm not saying that. I mean, I think, you know, falls in.
It's like Marty said, you know, what it could be just another form of matter. First you have the electron degeneracy, then you have the neutron degeneracy. So maybe after you pass the neutron, the Chandrasekhar limit, or it's probably the Oppenheimer limit. So you have another form of matter, but why is it not solid? with a solid surface. I don't understand where all this other stuff comes from.
Yeah, I think it's just ultimately like the equivalence principle. It's just that, you know, if you're just falling into a black hole, you know, the black hole, it's just a merely space-time phenomenon. And, you know, by Einstein's equivalence principle, like you would not know, you know, all things being equal, that you would even past such a threshold. You know, it just would be, you know, empty space for you. Someone far away would see something different. This, like, you know, I'm enclosed in a spaceship. I happen to be falling towards the Earth. You know, I don't fucking know that. But of course, you know, somebody else really far away sees my path curving towards, you know, the Earth or whatever.
Somebody far away does not see anybody or anything fall in, because the redshift is infinite by the time.
No, I just mean like they would see me, you know, falling towards the Earth.
Yeah.
But from my own perspective, it's just like I have no way of like locally knowing that I'm in a curved space outside of like tidal forces or whatever. So that for that very reason, it's like, you know, you pass the event horizon, you just, you know, you don't know it's there.
If it's a solid surface, you know it's there. If you fall towards the Earth, you hit the surface, you know it's there.
But I'm saying it's like, even if, you know, you're thinking about the matter that falls into it, like the matter curves space-time, and, you know, that's
It falls onto it, not into it. I don't see how matter can fall into it, because it is for a given radius, a given Schwarzschild radius, the matter that a black hole has is the densest matter that it can have.
Right, but that doesn't, as I say, and I got to go kind of soon, but it's like, you know.
So I don't know how additional
like,
matter can fall in. It's got to stick to the surface.
There's nothing incoherent about thinking like, suppose all that really dense matter is just concentrated at the center of the sphere, and it's curving space-time around it, and then there's
Only
like
mathematically,
gas
not in reality.
around it.
You know, with Newtonian gravity, you can assume spherical symmetry, and that the matter is constant. This is a mathematical construction. This is not.
I'm just saying there's no necessary connection between it being like super massive and like this idea that it's like some kind of solid object. I don't think anyone thinks that a black hole is a solid object. I mean, it is constituted by being, its nature is that of space-time curvature.
You could say that for any celestial body, that its nature is characterized by space-time curvature.
Well, yeah, I mean, sure.
But it doesn't mean it's not a solid object.
The difference is that there's a point of no return for the black hole, because, you know.
No, the thing is, as you add matter, it collects on the surface, and the density actually goes down.
Right, but yes, but the whole idea is that, you know, there's these two perspectives that, you know, stationary observer sees stuff collect on the surface, and person who falls in just sails right through. Well, we'll continue this argument.
Okay.
Yeah.
But
okay,
thanks for coming. Good chatting.
See you tomorrow if you can make it.
Yeah, hopefully I can. I may not be able to, but yeah, hopefully.
Thank you, Matt.
All right.
Okay, thank you.
Yep.
Bye-bye.
Take care, everyone.
Good evening.
Good evening.
Mhm.